Hello, sentient mammals. Let's jump right back in and finish up Relativity Part 2. In our first video, we talked about special relativity, which dealt with traveling near the speed of light and how that affects things like mass and length and time. Here we're looking at general relativity, which again allows for acceleration and gravity, where special relativity does not. General relativity says that space-time has geometry. It has a shape, it has a surface. And you'll see that in the picture on the left. A simple two-dimensional representation is a flat sheet that's made of grids like that. You can see like an XY grid almost on there. And that geometry is what special relativity describes in its math, is how does that geometry change as you do things within the space, particularly as you add mass. So the key part of general relativity is that space-time can be distorted. And you'll also see that distortion in the picture on the left. As there's large masses, moons, planets, and stars, they cause a warping of space-time, where you get these divots or these gravity wells in which these objects are placed. And that causes an effect on the space around it and on objects that are around it as well. So here is another example of how this distortion works. You'll see these two animated pictures here where you have the moon going around the Earth, and orbits are caused by this distortion, where you'll see it's like a marble circling around this divot as it goes around in a distorted space-time. On the other image, you'll see a three-dimensional representation of this distortion, how a massive body pulls space-time in towards it. So this is essentially what gravity is. Gravity is a distortion in space-time, and all the effects of gravity that we see are really just this distortion. You may have wondered in the past, we've done calculation with gravity, what is it, where does it come from, how can something on Earth have an effect on the moon without actually touching it or being near it? This is what's actually happening. The geometry of space-time is being warped so that there's an effect on objects in that space-time. Now, as objects get more and more massive, mass is the key factor that causes this distortion. The more massive an object, the more distortion there is. And we call the center of this distortion a gravity well. So you'll see in this picture you have an asteroid which has a very small gravity well, just a little bump. Then the moon is even deeper, and then the Earth is even deeper than that. If we kept going, you'd see the sun being really far down, and then as more massive stars go up there until you got up to black holes and then supermassive black holes, where you see these huge distortions going on. Key takeaway from this is that larger mass equals larger distortion. And the last thing to think about in general relativity is that light only travels in straight lines. This is actually known from special relativity, that light just travels in a straight line because light is always trying to get to its destination or to a target in the shortest amount of time. But what can cause light to quote-unquote bend is that a straight line is no longer straight if it's on a curved surface. So if you look at that moon circling Earth again, that sloped gravity well causes a bend. So if you try to go straight across that, you'll end up bending anyway. So light is actually still traveling in a straight line even when it's bending. It's just following the curvature of space-time. So again, curvature is an effect of the geometry. Now, this is in contrast to what we talked about in quantum mechanics. So why is quantum mechanics and relativity not matching up? Well, in everything else we've discussed so far, we've talked about particles. We talked about photons and protons and gluons. And to our knowledge, all other forces except for gravity are caused by exchanges of particles. The ones you see in the last column here, photons, gluons, Z bosons, and W bosons, are those force interacting particles that cause those forces in the universe. However, gravity appears to be significantly different. It's an effect of distorted space-time. We don't like that. That breaks our whole idea of creating that big theory. So this graviton here that's in this image, we wish there was a graviton particle to explain it, because that would make all of our theories work out. We could just have this chart and be done with it. But that's not how it works, because we have never found a graviton. We've tried to detect it, we've tried to find it, but we really don't even know how to find this particle in the first place. That doesn't mean it doesn't exist, but we're not sure how to identify it yet. But for contrast, the Higgs boson, the one right above it, was predicted in models for years and years prior, but was only discovered, experimentally found in 2012. And so since then, we've validated our theories and found that. So it doesn't mean the graviton doesn't exist, we just haven't found it yet. One of the effects of curved space-time is something called gravitational lensing. And this is a very cool effect that you need to think about and try to picture this in your mind. Think about driving down the highway in a car at 60 miles an hour. You're looking out the side window and it's raining. So picture this in your mind. What direction are the raindrops going across the windshield? If you picture that water streaking back, it's streaking from the front of the car to the back because you're traveling forward. So the rain is kind of pulling horizontally after it hits your window. But that doesn't mean that the rain came horizontally. It's not like it's flying at your face. It came straight down and then angled. So we know that the rain came straight down and then angled once it hit the car. But if you were to trace back a line from that rain going horizontally, it would point straight out toward the horizon instead of straight up from the cloud it came from. So we just know better. Light kind of does the same thing, except we don't know better when we look at it. So here's an animation of this gravitational lensing effect. What happens is that light from an object bends as it goes around a very massive heavy object that space-time distortion causes to go around it. And those light rays bend and come back in. So when we look at those light rays, we can actually get duplicate images of the same thing. The object might actually be completely hidden behind the really massive one, but we see two copies of it because it bent around them. And we don't know that those aren't the real objects. We just see the light from those objects as if they had come in a straight line, but they had really curved around the gravitational well of the larger object. And so here's some real images of gravitational lensing happening. Here you'll see this distortion where you've got, in the upper left picture, you'll see that you've got this central star, and there's an object behind that star. Fairly in the center, actually, right behind it. We can't see that object, but as light goes around that star, whatever this bluish object is, maybe a galaxy, probably a galaxy, it goes around it and the light bends in and we get this little halo effect of all the light from that galaxy. And you'll see that this is a very common effect in the universe. The picture on the right shows it happening everywhere, and there's clearly a very large, massive object here that many of these light waves are being distorted around. So this is gravitational lensing, as if it had gone through like a physical lens that you would have in your glasses or a magnifying glass. The light moves as if it was in a physical lens, but it's being caused by gravity instead of a piece of glass. Okay, so that's gravitational lensing. Before we continue, I'd like you to watch another video from someone else that's a summary of the couple of things I just talked about. So if you look down in the comments, there's or in the description, there's a link to Professor Dave's video on general relativity. So please watch that before we go forward. It'll give you a good summary of this topic. Another very cool effect from this idea that space has geometry that can be distorted by highly massive objects, or really any massed object, is the idea of gravitational waves. Now, gravitational waves occur when massive objects and highly powerful events cause space-time ripples to go outward. You'll see an example of this here on the right. Here we have two massive objects revolving around each other. These could be neutron stars, or they could be black holes going around each other. But the idea here is that as they're moving around and passing through space, they're sending out waves as if you would drop a pebble in a pond. So imagine those waves of dropping that pebble in the pond and them going outward. Gravitational waves are very weak, and they get even weaker as they go out as the gravity spreads out over a larger distance, just like those ripples in a pond. Now, we have built detectors here on Earth that are always working to detect these gravitational waves, but our equipment has to be so sensitive to make sure we don't get any false positives, and we are detecting gravitational waves from events like these revolving stars Or in the other case, something like a supernova, or the case of two neutron stars colliding, but these very massive high energy objects can cause singular ripples that go outward, and then we can detect those ripples later on. And this is the idea of gravitational waves. The space-time just gets distorted and moves outward. The last topic for this lecture is on black holes and how that relates to general relativity and the idea of distorted space-time. Now, we talked about this before we went on break, and we even watched a sci-fi episode on black holes, but I want to define it a little more clearly so everybody understands what a black hole is. A black hole is made of two parts. The first part is the singularity, and the singularity is created from the mass of a collapsed star. Now, after a star goes supernova, it may create a neutron star. And that neutron star, then, if it's massive enough, may collapse into a black hole. And what that means is that the finite mass of that neutron star, it has a specific amount of mass in it, will then collapse into an infinitesimally small volume. It goes all the way down into a point. It no longer has 3 dimensions to it. It actually gets condensed down into a single point. And that single point then, since you have a finite amount of mass in an infinitely small space, the density becomes infinite. And so that means you're going to have a massive gravity well, which you'll see here on the right. You have examples of the sun, and then a little bit deeper of gravity well is a white dwarf, and then a neutron star, which is really deep, but then a black hole is the deepest of all, that goes all the way down until it gets to the point that it actually tears a hole in space-time. So having all that mass condensed into a single zero-dimensional point, just a single point, that actually creates a tear in space-time. The second part of a black hole is the event horizon. Now, an event horizon is a non-physical thing. It's just a distance from the singularity that's dependent on how much mass is inside of it. But the boundary of where the inside of the black hole is, the event horizon, and the outside of the black hole is defined by a particular quantity. And that is the escape velocity is the speed of light. And what that means is, we talked about the escape velocity in the first cycle of physics. Escape velocity is the velocity you need to escape the gravity well of a planet. We didn't use the term gravity well, but to escape permanently from the gravity of a planet or a star, or it doesn't matter what it is, how fast do you have to be traveling to escape? Well, at the event horizon, the escape velocity is the speed of light. Now, we already know from special relativity that you can't travel at the speed of light. Only light can travel at the speed of light. So at the event horizon, at that point, nothing can escape. There is no way to get out of a black hole. That's why they say everything that goes in can't come out. You're sucked in, and that's it. You're there forever. And that's the way this works. An escape velocity of the speed of light, because there's no way to go faster than the speed of light to get out of it. So you end up being sucked in permanently. At the event horizon itself, time stops. So the space-time distortions become so extreme, the escape velocity is the speed of light, and time comes to a stop. It's very slow right near it, and it slows down as you get closer and closer to the event horizon, but at the event horizon itself, time comes to a standstill. So if you were an outside observer watching someone falling into the black hole, if they actually got to the event horizon, you would see them frozen in time forever. It's a terrible way to end, but not as terrible as the other thing we talked about, which was the idea of spaghettification. This is a proper scientific term. It's a great fun word, spaghettification, which means tidal gravity pulls apart matter piece by piece until it is only a string of molecules. So the difference between gravity between your feet and your head becomes so strong that it actually rips them apart because the forces are so different. And then the parts of you that are left, your arm will separate apart, and then your fingers will separate apart, and eventually that'll keep separating as you get closer and closer to the event horizon until even the molecules connecting your body together get pulled apart into just a string of molecules. So you'll never actually get to the event horizon. Now, I will caveat all of this with, we are talking about non-spinning black holes. When you have a spinning black hole, some interesting things happen with the event horizon that allows the singularity to become exposed depending on the direction you're looking at. So the event horizon is not a total sphere around the singularity. When it's not spinning, that is the case. And that's all we're going to talk about for this class as a whole. Now, Cool things happen with this. You'll see in the animation up in the upper left-hand corner that light is so bent around it that there's what's called an accretion disk. It's a flat disk of dust and gas around the black hole. And as that dust and gas travels behind the black hole, the light from it gets bent around it. And so you actually get to see that dust and gas behind the black hole as it comes over as its light is bent over the top and underneath of it. And that's what you're seeing in the picture in the upper left. Okay, the very last thing that a black hole, we can talk about with black holes, is theoretically, and this is pure theory, they may create wormholes. So if you have two ends of this gravity well of the black hole, they both have a tear in space-time, it is conceivable that two of those ends could flop together and connect with each other, creating a bridge through space-time. And conceivably, you could travel through that bridge. Again, this is theoretical. We don't know what's on the inside of a black hole. We don't know if this is really possible, but we think it might be. So those tears in space-time, the holes that are created by the black hole, can connect with each other and create a bridge through space-time to different places and times. Summarizing what you just watched in this lecture, gravity is a distortion of space-time, which explains how objects can affect each other over a distance. But it is not an exchange of particles. In fact, we've never been able to find the graviton particle as much as we would like to. So our explanation for how gravity works and how it affects objects over distance is through this distortion of space-time. Massive objects create these distortions, and they're in what we call a gravity well. Light follows these distortions. Light can only travel in straight lines, but what is a straight line on a curved surface? Light will follow whatever that path is over the curved surface. And some cool effects of understanding general relativity is how gravitational lensing works, that light gets bent around other objects and you can end up seeing multiple copies of the same object in the distance, or kind of like this halo effect where the light gets bent around. Gravitational waves are created by objects that are revolving around each other or by massive high energy events. And then you have black holes and wormholes, about how black holes are a finite amount of mass in an infinitesimal space that create infinite density and cause a tear in space-time. And the event horizon is the place where time stops and the escape velocity becomes the speed of light. Theoretically, it is possible for these holes in space-time to end up connecting with each other and creating bridges through space-time, which would allow us possibly to travel through them and cut down travel times across the universe greatly. Okay, that is the end of the lecture. Thank you for your time and have a good night.